Hey, good morning, everybody. This is Mr. Ainsworth, and we're going to get into section 2 here, part 1, and talk about what's called a linear growth model, which deals with arithmetic sequences. So let's get right into it. A linear growth model is where the population changes, whether it increases or decreases, all right, by a constant amount. All right, and we call that the common difference, by a constant amount in each transition. That indicates that you have arithmetic as opposed to, let's say, geometric or exponential. All right, so let's get right into an example and see what it looks like graphically and algebraically here. So a city here is considering a new law to restrict monthly amount of garbage allowed in the local landfill to a maximum of 12 tons per month, or a month, which is per month. Okay, so that's obviously important. So a maximum of 12 tons a month. All right, although there is currently only 800 tons of garbage in the landfill. Ooh, okay, that's another good piece of information. There's currently only 800 tons. That sounds like a starting amount. It kind of sounds like the seed, okay? So there's your seed right there, all right, which I'm talking about P sub 0. That's 800. So we start off with 800 tons of garbage in the landfill, and there is a concern that the landfill will reach maximum capacity of 2,000 tons. So that is important too. So maximum capacity, 2,000 tons. Determine the transition and the transition rule for the growth problem. Okay, so let's go back up here. Let's take a look at this piece of information. So it says the local landfill can take a maximum of 12 tons a month or per month. Okay, so first of all, this tells me right here, it tells me the transition. Okay, it's every month. Or you can say per month. All right, and we're going to be, it can take a maximum of 12 tons per month. So our transition rule looks like this right here. It says P sub n, where P sub n is the number of tons here, is whatever the previous month plus 12. All right, you can add a maximum plus 12 tons per month. So it's going to be the previous month, P sub n minus 1, all right, plus 12 max more. And again, P sub n stands for the number of tons per month. So let's go ahead and generate what's called a population sequence, first thing here. And again, a population in this respect is the number of tons. So population is in general can be many things, and it depends on the context of the problem. It's not always people, like people refer to. Okay, now the population, or the number of tons, we start off with currently 800. So P sub 0 is 800 tons. All right, you can add a maximum of 12 tons per month, a maximum of 12 tons per month. So let's assume they do, right? So after 1 month, that's P sub 1. This is after 1 month. We'll call that P sub 1. We have this plus 12. Well, 800 plus 12 is usually 812, right? And let's do this, let's go through 4 transitions here so we can just take a look at what the population sequence looks like. So P sub 2, well, that's 812 plus 12 more, right? Which is 824. And after 3 months, or 3 transitions, you have 12 more tons in there. We're assuming we're putting in the maximum. And so that's 836 tons, right? And after 4 months, there's 12 more tons in there. Well, 836 plus 12, well, that's 848. So 848 tons. All right, you keep adding 12. That's what it means by a constant amount. So let's go back up here. Arithmetic sequences and linear growth models deal with adding a constant amount. And that constant amount in this case is right here. All right, it's a maximum of 12. All right, so you take the previous month and add 12. There's your transition rule written recursively right there. And remember, this right here represents your previous term. Your P sub n minus 1 is just the previous amount, or the previous term in general, right? And then plus 12 in this case, because you're adding a maximum of 12 per month. Next, we want to plot and connect the points in the sequence and show that it's a linear growth model. It acts like a line, right? It's linear. All right, so what we're going to do is we're going to put the transitions here on the horizontal axis. All right, and that's going to be terms of n here, where this is P sub n, right? So we're in 0, 1, 2, 3, 4, 5, 6, 7, after 7 transitions here. And on the vertical axis, well, these populations, well, this refers to tons, right? This is tonnage. All right, so let's put tonnage right up here. All right, so tons, you can say tons or tonnage. And then we got to figure out how to scale the axes and then go for it. So since our initial amount starts at 800, I'm going to put a break in the graph right here, and I'm going to start at 800 here at the seed. All right, you don't have to start, go from 0 to 10, 20, 30, 40. Otherwise, we won't even have enough room. So I'm going to pick a scale of 12. I'm going to go by 12s. Let me erase this and put it a little bit over here. There we go, tons. And so we've got transitions on the horizontal, and we got tons on the vertical. So we're going to go by 12s. And so the scale here, or the distance between the grid lines, is 12. So plus 12, so 812. All right, then 824. It kind of makes sense since our constant difference is 12. And then 836, and then 848. You add 12 more, and then you're at 860. All right. All right, so let's plot. So when n equals 0, we get p sub 0. All right, so 0 comma 800 is right here. 0, 800. Come on. There we go. When after one transition, you have 812 tons. After two transitions, you have 824 tons. After three transitions, you have 836 tons. And after four transitions, you have 848 tons. Okay, and of course, you can take a straight edge out and understand that this is linear. Okay, it's a linear function. And when I say linear, all right, that implies that you have a straight line. So all arithmetic sequences or linear growth models are linear, and they all line up on a straight line. Okay, and from that, not only can you plot and connect the points in the sequence, you can answer the next question, which is what type of graph? What type? Well, it's linear, right? And so let's state that it's linear. All right, and because of that, you can write the equation of the line. All right, it's a line. And because if it's a line or it's linear, you know that it behaves like y equals mx plus b, because back in algebra 1, all linear functions act like that. This is slope-intercept form. All right, where m is your slope, m equals slope, and then b equals your y-intercept. All right, so what is the y-intercept? Well, it's wherever it crosses the y-axis, which is right here. There's your y-intercept. All right, and your y-intercept is 0, 800. Or b is 800 right here. So we know what that is. What's your slope, right? Well, that slope is rise over run. So we can go run this way and rise this way, right? And the distance between 1 and 2 is 1, and the rise between 812 and 824 is 12. Oh, so right here, it looks like your constant difference here is 12. That's your slope. So slope rise over run. In this case, it's 12 divided by 1, or 12. And that's in y equals terms of y equals mx plus b. That's m, the m value. So we know what m is, we know what b is, and so we can write the function. And so y equals 12 times x plus the y-intercept, which is 800. So let's kind of translate here. In terms of, we're not usually using y and x, we're using actually p sub n. So this is p sub n, right? And this is n. Instead of the x-axis, it's the n-axis for transitions, right? Instead of the y-axis, it's p sub n. All right, so p sub n is equal to 12 times n plus 800. There's your explicit function right here. Okay, where n stands for the number of months that have gone by right here, and p sub n represents the tonnage. All right, or you can say number of tons. Number of tons. If you don't like tonnage, you can say number of tons. All right, so now let's use it. Let's answer some basic questions. All right, how much garbage will there be there, or will there be in the landfill 5 years from now? Okay, 5 years from now. Well, the question is, how many months is 5 years? So 5 years equals how many months? All right, well, we know that there are 12 months per year, right? So what's 5 times 12? Well, that's 60 months. And you need to know that because n is not in terms of years, it's in terms of months. So to figure out the number of garbage, which is in tons right here, this right here is your p sub n, your amount, or tons. you got to find the y value or piece of n value when n is 60. So let me write the function here. So it's p sub 60. So that's p sub 60 is equal to 12 times 60. All right, plus 800. All right, and like always, you could do this in your head and multiply 12 times 60, which is 720, and then add 800 to get 1520, or you can kick in your calculator and do a little calculator work if you can't do it in your head. No worries, so use it when appropriate. All right, so we have 12 times 60, all right, which is 720, and then you have to add, oops, not multiply, but add 800, should give you 1520. All right, so that's 1,520 tons, okay, after 60 months. After 60 months, okay, or you can say 5 years. All right, 5 years, 60 months, same thing. That's your first basic question. So we use the models. This is called the model, the growth model. We use the growth model to predict the future, right? Because we don't know what's going to happen, but we use it to predict the future based upon the present values. All right, next one. It says how long? How many months? So number of months here. How many months have gone by when it not reaches the maximum capacity, but it's not 20,000. It is actually 2,000. Let's change this. The maximum capacity is 2,000 tons. Max capacity. If you look back at the problem up here, max capacity was not 20,000 tons, it was 2,000 tons. So that was a little typo right there, so let's change that. All right, so that is a piece of n value. Okay, so let me write the function here. So piece of n equals 12n plus 800. All right, this value here is it's not the number of months, it's actually a piece of n value. So when is 2,000 equal to 12 times the number of months plus 800? Well, we got to solve for n, which is the number of months, which we can convert to years. So let's subtract 800. Oops, 800 only. Okay, you get 1,200 equals 12n. All right, divide by 12. All right, and n is equal to 100. Excuse me, I didn't do that correctly. It's not equal to 100. What am I doing here? So, yeah, I guess I'm doing that right. 800, 1,200, yeah, okay. And so from here, we got, this is months, we want to convert to years, right? So we got to divide this by 12. So 100, all right, divided by 12. How many times does it divide in there? So let's just do it the easy way. So 100, all right, divided by 12, because there's 12 months per year, is 8 1/3. So actually, let's do it this way. So 8 times 12, 96. So that's 8 4/12. All right, or 8 1/3 years. And a third of a year is 4 months. So this is 8 years, 4 months. So 8 years, all right, 4 months, it'll reach maximum capacity of 2,000 tons. There we go. All right. Okay, so in summary here, a linear growth model produces what's called an arithmetic sequence. Okay, arithmetic. Oops, got to spell that right. So arithmetic sequence. All right, and the difference between terms in the sequence is constant. Okay, we know that by adding or subtracting here. This constant amount that we are changing the consecutive terms by is what's called the common difference. Okay, this should sound familiar because this is what we discussed in the previous unit. And that constant difference is called d. In this case up here, the constant difference was 12. The initial population that in any problem right here is the seed, which we call p sub 0, or the initial value. Okay, of the arithmetic sequence. All right, that's just a little summary of what we've done so far. All right, now let's generate a few more things that we need. Okay, we need to get an explicit function. All right, so what is that? A recursive function deals with the previous value. Okay, what happens if we need a function to predict the future without knowing any previous values? Okay, that's called the explicit formula. All right, but first let's play with the common difference d. And let's recall from previous lesson here. So let's say recall, I like to say recall, okay, that d is always equal to a2 minus a1, all right, from the previous chapter. We already know this. Okay, so because of that, right here, well, I should have put it right here. In this case, d is equal to, okay, p1 minus p sub 0. I've got to translate here. The first population minus the initial population. Or in general, we can say that p sub n minus the previous one, p sub n minus 1. All right, this is how I defined it before, a2 minus a1. All right, but we're in population sequences now, so let's translate it into our new notation right here. Where in the first example right here, p sub 0 is 3 and p1 is 7. So d in this case is nothing more than 7 minus 3 or 4, which kind of makes sense. You add 4 each time. Add 4, and so on. But what do you add here? Or what do you subtract? Well, let's calculate it. So d is equal to negative 11, the second term, minus the first term, right? Minus a negative 4. Simplify a little bit, cancel out your negatives. Negative 11 plus 4 is negative 7, so d is negative 7. There's your common difference. All right, you simply subtract 7 each time. Okay, on this one right here, d is equal to 97 minus 123. So d is equal to what? Ooh, you either do it in your head or you do it on your calculator, one of the two. All right, you take 97, subtract 123, and what do you get? Well, you get negative 26. Right, negative 26, and that's what you subtract to get to the next term. There's your constant difference right there. So recursively, all right, for any arithmetic sequence right here, p sub n is always equal to, all right, the previous term, p sub n minus 1, all right, plus the common difference, plus or minus the common difference. Just like in the previous problem, like right here, you take the previous term, add that common difference to get to the next term. All right, so in general, any arithmetic sequence is found by taking the previous term, add that common difference. Remember that d right here is called the common difference. The problem with this is that it's not very useful to predict the future values if you don't know the previous ones. So we need another formula called the explicit formula that deals with the seed only, which is your starting term, and the common difference. Okay, so we can predict the future. So watch this, we're going to develop it. Okay, so p sub 1 is equal to the previous term, p sub 0 plus d, from the recursive formula. That we know. And what I want to do is develop a function, what's called an explicit formula, that deals with the seed, which is p sub 0, all right, and the common difference. So let's develop it. So p sub 2 is equal to p sub 1, the previous term, plus the common difference from the recursive formula right here. Okay. But I want to express each one, p sub 2, p sub 3, p sub 4, in terms of the seed. And right now it's not in terms of the seed. It's in terms of p1 right here. But what is p sub 1? Well, this right here is found above by taking the seed plus d. So this right here, let's replace it with what it's equal to. Well, it's p1 is equal to p sub 0 plus d. So let's substitute that in. So p sub 0 plus d. And then, so I just substituted that in. Right, and then add another common difference, right? Add that common difference there. Well, adding like terms here, I see d plus d, and that's 2d. So this whole thing equals p sub 0 plus 2d. I want to do that for each population. I want to re-express the population in terms of the seed, the starting term. Remember, this is the seed, because you're always going to be given that. All right, so what is p sub 3? Well, p sub 3 is equal to the previous one, p sub 2, plus the common difference. But what's p sub 2? This right here. Well, I just found it. It's the seed, p sub 0 plus 2d. So let's replace it. So p sub 0 plus 2d, and then plus another d. Adding like terms, which are right here, 2d and d, that's obviously 3d. So you get p sub 0 plus 3 times the common difference. So notice that I'm re-expressing each population in terms of the seed, the starting term. All right, I'm going to do it one more time, then I'm going to generalize. So p sub 4 is equal to p sub 3 plus the common difference. We always know that it's always the preceding term plus the common difference. Well, what's p sub 3? Well, I found it earlier. I found it. It's p sub 0 plus 3d. So I've got p sub 0 plus 3 times d plus another difference. And if you add the like terms, 3d and d is 4d. So you got p sub 0 plus 4d. So notice here that the subscript corresponds with the coefficient right here. So if you notice that, and you'll see that is a pattern, it's happening even here too as well, then you can re-express it. So here we go. I'm going to generalize it. So we have p sub n here. In general, is going to be equal to the seed, p sub 0, all right, plus whatever this value is. In this case, it's n times d. So n times d. And that's all there is to it. All right. And let's see, you're going to be given the common difference here. So I'm going to just rewrite this here a little bit here. So p sub n is equal to p sub 0 plus d times n. So let's highlight that. This is what's called the explicit formula. This is what we use to predict the future. All right. If we know the seed and we know the common difference, which we're going to be given, then we can predict any term in the future by using this formula here, even though we don't know the preceding term. So the recursive formula is good, but it's not useful all the time, all right, if you don't know the preceding term. So what do you use? Well, you use the explicit formula. The explicit formula is what you use, all right, use this to predict, all right, the future. All right, so let's continue. All right, let's do two things. Let's write the recursive formula here first and the explicit formula second for each of these sequences here. And notice that right here, p sub 0 is 7. So that's the first thing you notice. All right, p sub 0 is 7. All right, that's p sub 0, and p sub 1 is 13. So once you know that, then you calculate the common difference. So it's just 13 minus 7. All right, so d equals 6. And so recursively, all right, what you have is p sub n is equal to, all right, it's always the previous term, which is p sub n minus 1, plus that common difference. There's your recursive function. And your explicit function, which is right here, it's always the seed plus the common difference, which we know. So p sub n is equal to the seed, which is 7. Look right here in the sequence is the starting term. All right, plus d, which is 6, all right, times n here. And there we go. There's your explicit formula. So this first set of examples here just teach you how to write the formulas, and then the next set of examples on the next page are going to tell you how to use them, or are going to show you how to use them. All right, so here we go. Let's get some experience. So we know that p sub 0 here is -3. D is equal to -1 minus a -3. If you simplify a little bit, you get -1 plus 3 by adding the opposite. -1 plus 3 is 2, so the common difference is 2. Okay, and then we got recursive function here, and then we got to write the explicit function. So recursively, it's always equal to the previous term, all right, plus the common difference, which in this case is 2. Explicit function, p sub n is equal to, put this up here, the seed, which in this case is -3, all right, plus the common difference times n. So it's always d times n, so d is 2. So 2 times n. All right, let's get some experience. So on this one, p sub 0 is 2, d is equal to -3 minus 2, so d is -5. So the recursive function is p sub n equals previous term, p sub n minus 1, plus the common difference of -5. Or you can write it just as -5. And the explicit function, p sub n, is equal to the seed, which is 2, all right, plus d times n, so -5 times n. And if you simplify that, it's just 2 minus 5 times n. Plus a -5n is the same thing as 2 minus 5n. Okay. Next one, the seed is -3, d is negative 6 minus a negative 3. So the common difference here, if you simplify, is negative 3. So the recursive function, p sub n is equal to the common difference, p sub n minus 1, plus d, so plus negative 3, or just simply a minus 3. And explicit function, you start with a seed of negative 3, seed's right here, plus d times n, so plus negative 3 times n. So if you write it like that, or you can simplify it, p sub n is equal to negative 3 minus 3n, which is the same thing. Okay, most people write it this way, all right, when the common difference is negative. Okay, the next, what you want to do is learn how to predict the future. So on the next page here, we do that. So we first write the explicit formula first, because that's what predicts the future right here. So that's step 1, okay? And then step 2, right here, we want to solve for the given term. All right, so we first write the explicit formula. So let's write that up here, big and bold in red. So p sub n is equal to the seed plus d times n. There's your explicit formula. Okay, big and bold. So up here we know the seed, we're given the seed right here. We're given the common difference. All right, and this is what we want to find. We want to find the 16th population after 16 transitions. So first we write the formula first, okay? So p sub 0 is 8, so it's 8 plus 3 times n. Now to find the 16th population, where n equals 16, like right here, n equals 16, you simply substitute your value into your function. Whatever n is, you substitute that in your function. So you take 8 plus 3 times 16. So what is that? Well, it's 8 plus 48, right? And so you can work it out. 3 times 16. All right, that's 48, and then you add 8 more, so add 8 more, and you get 56. And that's how the game is played. And you just have to continue and get good at it. You write the function, and then use it to predict. And so here, the function right here, on this one here is the seed, which is 5 plus negative 2 times n. And then you want to find p sub 14, which is the 14th population. So you substitute 14 in, so it's 5 minus 2 times 14. Notice I switched right there. Plus a negative 2n is the same thing as minus 2n. And so you enter that in, 5 minus 2 times 14. All right, and that's 5 minus 28, or negative 13, or excuse me, negative 23. 5 minus 28 is negative 23. So you just do a little, you do a little practice here, and you get really good at it. Okay, so notice on this one now, the d is not given. So d is equal to 5.9 minus 5.3. So what's that? Well, that's just 0.6, right? So d equals 0.6. So p sub n is equal to p sub 0, which is 5.3, plus 0.6 times n. There's your function. Now let's predict what the 39th population is going to be. So 39 is equal to 5.3 plus 0.6 times 39. You know, kick in your calculator. So 5.3 plus 0.6 times 39. And you get 28.7. So if they don't give you the common difference, you got to find it, right? Like here, I know the seed, but I don't know the difference, so I find it. 8 minus 5 is 3. So my function here, p sub n, is equal to the seed of 5 plus 3 times n. And then after that, then you find what you're looking for in the 41st population. So p sub 41 is equal to 5 plus 3 times 41. And let's see, what's that? 5 plus, all right, 3 times 41, and you get 128. All right. And that's all there is to it. All right, so let's end with a word problem here. All right, here's a classic example dealing with Java. Okay, coffee. It's a coffee shop. It opened 2005. Right here, there's your start. All right, 2005. with 370 coffee shops. Okay, there's your C to P sub 0. P sub 0 equals 370. So notice how I outline the problem as I read it. And it plans to open 60 new coffee shops per year, each year. Okay, there's my transition time after that. So it's 6 to open up. When you open up 60 new coffee shops, you're adding 60, or it's increasing by 60 every year. So there's your common difference, or your transition. Okay, so if you want to understand this situation, here's your population sequence here. Okay, you start off with 370, right? You start off with 370 right here. That's your seed. And then you add 60, right? 370 plus, all right, plus 60. Well, that's 430. Add 60, 490. Okay, you add 60 every time, right? And then add 60. What do you get? Well, you get 450, right? Excuse me, 550. Obviously over 500, so 550. All right, etc. So this right here, 60 is your common difference. All right, so as a population, as an explicit formula here, which is what they want. All right, you have P sub n is equal to the seed, which is 370, plus the common difference, what you're adding, times n. And then you get to use it. So, how many coffee shops will there be there by 2020? Well, if you start in 2005 and you go all the way to 2020, right there, how many years have gone by? Well, how about 15, right? 20 minus 5 is 15. So 15 years have gone by. So what you need to do is you need to find P sub 15. All right, and what is that? Well, use it. So it's 370 plus 60 times 15, and then you work that out. So 370 plus 60 times 15, and you get 1270. So 1270 coffee shops. All right, by in 2020. Okay, and then in what year will the, that's N now. So what year will they reach 2,000 coffee shops? All right, so what we need to do, this is right here, that's your P sub n value. So when, after how many years will it reach 2,000? So 370 plus 60 times n. So n is the number of years here. So when we say what year, n equals what, right? So, so you got to solve this equation. So you got to subtract 370. So let's do that, and you get, well, let's see, 2,000 minus, I'll do it you can do it in your head, but let's just do it this way, minus 370. Get some values here, so 1630. All right, that's equal to 60n. Divide by 60. So divide by 60. And you get about 27.17. So what was that? 27.17. So 27.17 years, okay, after, all right, the starting year, which is 2005. Okay, so if you add 5 and 27, so that would put us in year 2032. So 2032, roughly, approximately 2032. All right, and what year? Okay, 27, a little over 27 years after the starting year of 2005. And that's how the game is played. Now, there's more to it, of course, and that's in my next lesson. All right, but right here, that's how the game is played. And at this point, you can probably, you can start doing your homework if you like. But the question is, do you understand it? If not, go back. It's a video, so go back and replay it if you need to. It's a pause and play video, so go at your own speed, practice, and get the nuts and bolts and the basics down so you can handle the future lessons, okay? So this is all about linear growth models or arithmetic sequences in section 10.2, part 1. Okay, this is a 2-part video. All right, this is part 1 dealing with linear growth models. All right, and this is Mr. Ainsworth. I'll see you in my next lesson. Bye-bye.